Okay, we're up and rolling for Wednesday, the 3rd of February. I didn't bring the sound system down here because I decided I won't do that for a couple of more days. Maybe next Monday I'll do it again. But the sound demo that I did last time is sort of a precursor to what you're going to be doing a week from this Friday. The next lab you move into, you'll be using headphones. So if you have your own iPod, headphones or whatever, you can bring those in with you rather than using the ones that I can sign out to you to use during the lab session. But you'll be creating waveforms and listening to them, and part of what goes on in the next lab is listening to things, creating certain types of waveforms. So one of the items we didn't look at with the tuning fork of last time, we listened to this tuning fork over the sound system. We looked at its spectrum, and I looked at it in a MATLAB environment called SP2O that I ran last time. And you can see how I ran that by looking at the video from last time. But another built-in calculation is to use MATLAB's PSD function, which stands for power spectral density. I may have you explore this in a project towards the end of the semester, maybe not, I don't know. But at any rate, it displays the spectral content or the frequency content. And that's really what the first part of Chapter 3 is that we're going to launch into shortly. But we looked at this briefly last time, and we know that the tuning fork was supposed to be at 440 hertz, and it nominally was there, but then it had another spike at 880. And in this particular plot that I generated using the PSD function right from the MATLAB command window, we see a whole lot more harmonics than I displayed to you at the end of class last time. When I say harmonics, I mean multiples of 440. That's a terminology that engineers use a lot, and we'll be using that in Chapter 3. So we see there's other tones embedded inside of that tuning fork when it's ringing. It doesn't ring just at the fundamental. And those of you that play guitar, and I'm sure there's somebody in here that has at least played a guitar once in their life, when you pluck the string on a guitar, it doesn't put out a single pitch. It's not that boring sounding. I mean, a single pure tone is actually pretty boring sounding. In music, if all musical instruments produce just single tones, single sinusoidal tones, the sounds would not be very exciting. That's my contention. Instruments have a certain timbre is the term that they use, meaning that they have a collection of harmonics that make up the whole pitch that you listen, or the sound that you listen to when a note is played. And that's what gives it the color that makes it interesting. Unless you're not very interested in music, I would say, that's something that you actually makes it interesting. So we'll go on and explore that more in the next chapter. But another dimension of looking at the signal, this plot right here is called the time domain. Meaning that we see the wave shape as a function of time. We started off just a couple weeks ago looking at the cosine wave and saying, oh, in trigonometry, that was just a function, right? Just a plain function of some argument in radians, and it produced an output that varied between -1 and +1. That's what the cosine function does. And you know it's related to geometry and triangles and stuff like that. But in signal processing, the cosine wave is a fundamental waveform that we use for radio communication, acoustical testing, and just modeling and representation of other more complex signals. So we have generators in all of the labs, and all the lab benches upstairs have generators that can produce a cosine wave. In other words, a signal that looks like this that fluctuates up and down as a function of time. And on Friday, I'll do a demo for the direction finding part of the lab that will produce that waveform through a speaker, and then I'll be picking it up on 2 microphones, and I'll explain a little bit of that later before we leave today. But at any rate, the time domain is when we look at the waveform as a function of time, and that's what we have going along in this axis. So that's called time domain. In terms of acoustically, what does that mean? When we listen to that sine wave, and you can think about what you know about sound waves from physics, high school and beyond, when we have a positive going wave, it's like the sound wave on our ears putting positive pressure on our eardrum, and when it's a negative value, it's pulling the eardrum out in the other direction. So it's compression and expansion of the molecules in the air around our eardrums, right? Remember that from physics? But electrically, we have this electrical representation, which that could be a voltage, it could be a current in a circuit, it could just be a number stored in the computer after we've processed it into MATLAB. And that's what I did here. I processed it through this microphone right here, hit the tuning fork, held the microphone there, and recorded it using a WAV file recorder. How many of you have played with recorders on the computer using some sort of WAV recorder for WAV files? Anybody? Okay, some of you have. Or on the Macintosh, it's something similar, but you will effectively be doing the opposite of that in the lab. You'll be generating sounds. But in some of the labs that I have in signal processing, we do exactly that. We record things and play around with a recorded wave signal. There's actually a senior design team that's doing that a lot right now. They're working for a medical products company up in Denver, and the theme there is what a stethoscope picks up off of a patient. So they're designing some algorithms to process the stethoscope signal and trying to minimize some of the impacts of what the stethoscope picks up when a person coughs, or if the stethoscope bangs against something, or if the person is talking. Apparently in the medical community, and I don't listen to stethoscopes, and unless you're a doctor, you probably don't either, right? But doctors are annoyed by loud extraneous sounds when they're trying to listen to patients and hear certain attributes going on in their chest cavity. So that's an example of signal processing, trying to work that signal to improve it or enhance it. So this is known as the frequency domain, and this is chapter 3. And in the frequency domain, we get a representation of the signal versus frequency with amplitude on the vertical axis. So here we see just a different view, and electrical engineers are very intent upon having both time domain and frequency domain views of things, because now we see something that we can't see in the time domain. We look at the sinusoid over here and we say that looks like a pure sinusoid. But the spectrum analysis point of view can decompose it and see that, yes, it is dominated by this 440 hertz component, but when we put things in a logarithmic scale, which is what's done here with the dB scale, which I'll talk about later, that this next harmonic is down, so many dB on this dB vertical scale. It's not visible in the time domain plot, but in the spectrum plot it is discernible, and we can see that we have a second harmonic present in the waveform. It adds color to the waveform, but in a radio sense, radio waves, the Federal Communications Commission says if you were broadcasting a radio signal, say, at 440 megahertz rather than hertz, so it could propagate through space, the FCC would say you cannot propagate a second harmonic with much power at all. You have to have second and higher order harmonics down so many dB or dropped below so that they don't interfere with other radio users. Does that kind of make sense? You're listening to a radio station, and it would be very disturbing if another radio station had an extraneous signal coming off its transmitter that interfered with the radio station you wanted to listen to. That's downright bad. As a matter of fact, it's against the law. I mean, the FCC regulates that so we can all share the spectrum mutually. So the frequency domain view is very important in radio type signal processing. Somebody occupies one frequency spot, another person can't use it because we'd all get garbage. If two people are on the same frequency location with their transmitted signals, we get garbage, and no one's happy. Now, if it's a military scenario, that might be intentional, right? Somebody might be jamming another signal. But even so, then understanding the spectrum is important too, because then if you were going to jam signals, you'd want to know exactly where to pinpoint your jamming signal so you're the most effective. And that's the way things are done in military scenarios. Now we have let's see, what's the right term I'm thinking of? Some of you have maybe been in the military and used this terminology. There's measures, and then there's countermeasures, and then there's countermeasures, and it goes on and on like that. You see that in movies, though, too, right? We build this system, somebody figures out a way to defeat it, then you build another system to counter the counter, and then it just is a continual escalating of technology, and this is recorded throughout all time, right, in terms of systems to defend one nation against another's intrusion and so on. So it plays a role in studying systems for military applications. A third view is sort of a combination of the time domain and the frequency domain, and you'll be exploring this in the lab that starts a week from this Friday, and that's the spectrogram. And the spectrogram displays spectrum on this axis down here, but it also displays time, so it takes and forms what's called a short-term spectral analysis of the signal. So it takes the spectrum at each slice in time. And in this case, remember when you bang down the tuning fork, it has a little metallic sound, not the ringing of the tuning fork, but just an extraneous sound came out of it. I don't know if some of you noticed that. Before it settles into the nice humming sound, it had kind of a clattering sound. That's what's going on right in here. The spectral content has a bunch of other pitches in it. A very broad spectrum of tones comes out at low frequencies when it first was banged on the edge of the table. And then as time went on, when we got 1 second in, that went away, and then we just saw a strong component at about 440. A much weaker component is shown by a duller or dimmer red fading into yellow. And then we can see other bandings going up there, meaning that there's harmonics, but they fade out first. And 10 seconds in, we still have a pretty strong deep red color indicating a strong spectrum component at 440. So you're visualizing it, how the spectrum changes in time. And spectrograms are used to analyze speech patterns too, like with your vocal cords vibrate, you would see all the harmonics from my vocal cords, and each person would look a little bit different. Everybody in here, if they said a sentence and we analyzed it in terms of a spectrogram, would look slightly different. And you've probably heard that spectrograms can be used for identifying a speaker. I mean, if you have a recording of somebody captured here and then you record them, say, in a cell phone conversation, and you want to compare who was speaking, the spectrogram is kind of like a fingerprinting mechanism for an individual. I mean, yeah, I can raise my voice when I get excited. My pitch will go up. We can artificially move it up and down, but we tend to have a natural setting for our pitches in our vocal cords. Sound interesting or not? Question?
On the way here, I was thinking in the car, is there, so we can, if once we record our voice, and we have two recordings, somebody else's voice,
right?
Can't you make your voice sound exactly like somebody else's voice?
There could be some means. I'll just say this in the microphone. The question is, can we record our voice and then can we transform it to make it look like somebody else's? There is mechanisms for pitch shifting and breaking things out, so there would be a way with sophisticated algorithms to go in and move some things around. I mean, you can certainly do pitch shifting, and that we know is true. I mean, if you think of the American Idol show as an example of people singing, if you've ever watched that, people tell me that people in the music industry that sing, no one really has to be truly a perfect pitch singer anymore because of signal processing. We can bend pitches, we can make people sing in harmony better by processing a particular track of like one singer on one microphone, another singer on another, or maybe you record the track and then you want to record a harmony track over it on another channel and then you want to mix it together, you can do some pitch adjusting on that to even bring it into better pitch, which that suggests that you could get even more sophisticated and try to mimic another person's exact speech inflections. But that gets a lot more complicated because nobody's vocal cord and voice box and mouth and all that other stuff that affects it is identical, except maybe identical twins or something like that. Any other questions? I mean, this is just letting you know, and you're going to get a chance to play with the spectrogram in the lab, and it'll be interesting and revealing. You'll see how useful it can be for certain types of applications. Well, now what we want to do is jump back and go back to this, go to the worksheet that I've handed out. This was the ending theme that we kind of worked on Monday, of being able to take a sum of sinusoidal signals all at the same frequency. In this case, they're all at 440 hertz, and add them up to get a composite signal. This will be the subject of the quiz on Friday. There's many homework problems related to this, and just a quick flash, if I was to jump over to the next chapter, you'd see that beyond problems 1 and 2 on the homework, problems 3, 4, and 5 are all along these same lines. They're all phasor addition type problems. So I'm just pulling a variation on that out beyond what's on the homework to just have us work through it before we jump into the next chapter. So normally what I do, if I had a lot of time on my hands, which I generally don't feel like I ever do because I'm always rushing somewhere, I would break you into groups and say, let's work on this for a while and give me the answer. Instead, what I'd like to do today is just kind of get this started, maybe with some people helping me out, and then I'm going to leave it kind of hanging for a matter of hours here, and later tonight or early tomorrow morning I will post up my solution to this. I'll have a calculator-based solution, and then I'll have a quasi-calculator-based solution. I know from grading your quizzes already that some people know how to use their TI-89 or equivalent calculators very well. They slam dunk the quiz absolutely, and I'm confident that given enough practice at problems like this, it'll just be another complex arithmetic exercise, and you'll plug in and get it right away. Others of you know that you need work, so this is also going to continue to practice on that. This is a real live application of complex arithmetic, though. So remember what the idea is when we want to add up a bunch of sinusoids at the same frequency and form it into a composite, and that composite is just down into 2 attributes, a composite amplitude and a composite phase. What do we have to do first? Pardon me? We have to go into rectangular, but even before we do that, we have to identify what the underlying components are from each of those 3 sinusoids, right? We have some complex number. We have to identify, let's see, get the right pen on here. We have to formulate what x is going to be. And x is going to be composed of how many pieces in this case? How many x values do we have to come up with here? 3, right? So we have x1, x2, and x3. And we're going to be adding them together, so your comment about getting into rectangular form would be for the ease of adding complex numbers in rectangular form. So if we're going to go that way, then the first thing we have to do is identify what those 3 guys are. So working from the top down, what is x1? Somebody just tell me, raise your hand, and I'll call on you if you all want to dash to the same answer. x1 is the easiest one, I think. Okay? What is x1, starting from the top?
I thought x1 was 52 cosine, open parentheses, 2 pi times 400
No, x1 is the components of the first cosine. Remember the magnitude and phase? Remember that? Do I need to flip the notes back over and go look at that? Maybe I need to jump back for a second and just get you on this the right page here. If I was to scroll back up here in the notes, I had this summary in here, and the summary said if we're starting right there at step 1, we have a sum of cosine waves. Then we have to identify from that the components, which was step 2. The x1 is a1 times e to the j phi 1, and so on. And then step 3 is to write it as the final a cosine phi after you've added up the x values to get an equivalent a e to the j phi. Remember? So now if I jump back over to this worksheet, so you started off right, 52. What somebody else can step in. So what do we have for the first term here? What's x1? Okay.
E to the j negative pi over 4.
Yep. So he's just saying there's the amplitude of that first term. That's the A1, and that's the phi 1. That was the easy one. Now what's x2 going to be? And I'll clean this up when I put up the solution for it, but what's x2? Somebody else try for that. I've made this fairly complicated because I wanted to take a tougher case in my example. It won't probably be as complicated as this on the quiz, but okay.
Is it 12 times the quantity negative 3 minus j5 times e to the j 2 times pi over 6?
Yep. You got it. Now, does everybody else understand that? Because this is fairly convoluted, but I kind of hinted at that this could be done. I think what he's done, and do you have quick words to explain to the class, or do you want me to try to interpret what's on my mind? What you did to get that?
And then took the real portion, which is cosine.
Okay. So he said he used Euler's identity and recognize the fact that when you take the real part of that complex quantity in the curly braces, you get a cosine. So he's seeing already that, first off, what you could do is you could take that guy right there, that can go to a polar representation, right? So if that was in a polar representation, suppose it was a b e to the j, what's a good, e to the j, I'll just use alpha. That would be a rectangular to polar form. Then I could take and visualize that b as coming out of the real operator, and this j alpha in here would just jump inside of here as a polar form. So without even thinking about doing any more details on it, that's equivalent to just saying that in terms of the x1, it's just all written down here as its rectangular form, and then there's another piece to the phase that's sitting up in the complex exponential that joins forces with it. Or if that sounds too complicated, I don't know what I can think of other ways of looking at it, but I don't have it clearly in my mind. Does anybody else want to take a crack at how they would see it? This is kind of like what you have in the lab, though. There's something very similar to this in the lab. When you synthesize a signal, they have it set up kind of like this. I'm sensing a lot of deadness in the air, which tells me if I put this variation into the quiz on Friday, I'm likely to get a return of 0. In other words, I'll send out a pulse, a radar pulse, and my return off of that will be 0, like fully absorbed into the brain, but nothing woke up and responded. But if you were to go through Euler's identity, just like he said, you could crank it all out and it would come flying out of there. Because the real operator is going to recover what it needs to recover. I mean, the easiest way for me is to think, convert it to polar form, which is this guy in here, and then the B sits inside of there. So the B sits inside of here, and then stuffed in at the end of this is the alpha, right? Because I can do that with complex arithmetic. I can take, when I multiply polar form numbers times polar form numbers, what happens? The magnitudes multiply, so that's just a magnitude of B. And then the e to the j's, the arguments do what? They add. So that's why the alpha just adds up in here. And then when I take the real part of all of this B will just move to the outside because it's a real quantity. And the whole phase component that's going to come down is the pi over 6, e to the j pi over 6 plus alpha. So in reality, if I did that substitution right down in here, I would have times b times e to the j alpha, like I was just saying. So that would be equivalent. But I don't want to put that in here because I don't know what b and alpha are, so I just leave it as, for right now, I just leave it as minus 3 minus j 5. Okay, what about the last one? Okay, try it.
Is it 20J?
Well, it has to be an E.
20J e to the j pi. Plus, is j theta.
Okay.
I'm looking at this pi over.
This is the cosine guy.
Since it's sine, don't we have to take the derivative of sine to get cosine?
Well, we're taking no derivatives here, but remember that this is a trig identity, right? Cosine or sine of theta is equal to cosine of theta minus pi over 2. Remember that identity?
20 e to the j, and then negative pi over 8 minus pi over 2 would be.
Yep, that's right. It's a little bit messy the way I've got it written on the page because I'm writing it on my screen kind of vertically, which is, I'm vertically writing challenged on my tablet. I can't hold it steady enough, but that's right. So the next steps here, you have to add those up, and on a TI type calculator, you can just blast all of those complex numbers in directly. No needs to do any side calculations on that. If you don't have that type of calculator, then you have more of a challenge on your hands. And probably what I would do in that case is I would use Euler's identity. So on the first term, how could I break that into rectangular form just on paper here? What would the first term be in rectangular form? Okay.
52 times the cosine of negative pi over 4 plus j sine of negative pi over 4.
Well, yeah, there has to be a 52 in there, right? Unless I put the parentheses somewhere else.
My parenthesis was
Around the whole thing. Okay. It's the second term that's troubling, right? There's really no option except to just, take it head on this term. Actually, there are some options in there. What would one option be? Let's just see what another option might be. I'm thinking of a couple ways. Let's see if somebody else has an idea. How would you tackle the second term there? This is the first term. So how do we tackle the second term? What's one possibility anybody can think of? We basically have to multiply numbers, two complex numbers together, and we'd like to have it in rectangular form. So what's one way that somebody can see to write that down? It's not going to be totally pretty, but it's going to be a start in terms of progress.
Can't you distribute your 12?
You can distribute the 12 around the whole thing if you want to. And then you could go and attack that guy and say, what does that break out to from Euler's identity? What is that term all by itself from Euler's identity? Okay, cosine pi over 6 plus j sine pi over 6. Well, we're not finished yet. Now we can multiply in rectangular form if we want to. It's kind of messy, so what could I do right here? I could go ahead and do that. That's just more messiness, but I could blast through that if I wanted to.
3 goes with the cosine, the 5 goes with the sine.
But then there's two cross terms also, because it's multiplication, right? Term by term. So you're going to have to bring the minus 3 onto this guy and onto this guy, and then you're going to have to do the same thing with the minus j5, and then you're going to have to remember that j times j is equal to minus 1. So it's a little bit messy, but it can be done. The other approach would have been, like I said when I was hinting at how to break the problem up, you could just from the get-go say that this is b e to the j alpha, just convert it to polar form right then and there. And then the alpha would join with pi over 6, and the beta would multiply times 12, so you'd have a new polar representation of that term, and then you'd finally break it out using Euler's identity, using the cosine and the sine of the new angle. It's messy no matter how you do it. It's just the nature of this kind of work, which is why tools are important. They make life easier.
So then b would be the square root of 34. B would be the square root of 34 in that top one.
Yeah, it's 25 plus 9, so that's 34. I'll put some of those details in my solution. How about the last one? Last term. The last term can be expanded out using Euler's identity directly, right? So it's cos 20.
Is it division? Is that a bj by
Well, you just combine minus pi over 8 with minus pi over 2. So we have 4/8 for 1/2 and 1/8, so we have 5 pi over 8. Then we have a plus j 20 sine of minus 5 pi over 8. So then, presuming you were working like this with a calculator that doesn't have all the complex stuff built into it, you would then get all these individual numbers, you'd add up all the real parts, add up all the imaginary parts, and then you'd form the magnitude and the phase or angle from that. And then finally, when you get there, then you'd finally have, the A and the theta for the composite. Thad?
You said on the middle one, you foil that? I just want to make sure that
You can what?
foil it.
Yeah.
That's what you first do.
Yeah, you said foil?
Yeah.
Okay, haven't heard that term before. No. What's that?
First not really last, it's just an acronym.
Acronym.
Yeah.
Okay.
Multiply out two terms.
Okay. I just say complex arithmetic multiplication or multiply. Maybe I'm not hearing something correctly, though. My computer's fan is kind of running and blowing at me, a noise field. Yeah, multiply it out, and then you get 4 terms, right? Which is messy, but you can do it that way. What I would suggest you do, and you try this out, sit down at MATLAB. If you don't have the calculator that has the power, just sit down at MATLAB and get the answer that way. Or if you have the 89, get it that way too. But then if you don't have the calculator that works it all automatically, at least get the answer in MATLAB and then go through some sort of calculation like this and just see if things agree. I'm going to try not to be quite as intense on the quiz as I am right here, but I can't say that it won't be free of some special nuances that might just come up. Now, hopefully you can see that this is just, now using the skills from the previous quiz and the previous weeks to just apply to a problem. And then, things are building. So we're not just squirreling all over the universe. We've got a theme going here, and now we're going to start a new theme in Chapter 3. So look for the solution for this one to come up early tomorrow, probably. With regards to the homework, since I'm now going to jump over, why don't I just look at the homework right away since I'm on it. With regards to the homework, the first 2 problems are basically just sketching, and the second one is piecewise representation. That's stuff that we went through earlier last week. You guys sounded like you were confident on this because of what you've done in other math classes. So you can have MATLAB draw the pictures. You can just draw them on your engineering paper or neatly on notebook paper, especially for problem 1. Problem 2 is just the piecewise thing. And remember, I talked about how you just have to find the equation for the lines, those 2 segments. So you'll be finding, an AX plus B type of thing here, or in terms of the terminology, it's A times T plus B. And likewise, you have the equation for that line. That'll be part of the piecewise solution. Problems 3, 4, and 5 are just phasor addition problems, just like what we went through, except these are a whole lot easier. Like this one is easy, right? Just cosines, nothing fancy, so you can identify x1 and x2 directly. This one is a twist on it, but if you look at it from an algebra standpoint, is there anything special about it? You can just rearrange things and move A to one side, so there's really nothing special about that either. I just rearrange things, kind of like camouflage. Can you unravel it? Problem number 5 just adds in another term, and the sign variation is thrown in there. But then it also says write it as a complex term, and that just says, from what we've gone through in class already, we already know that the real part of A e to the j omega t plus phi reduces down to A cosine omega t plus phi, right? From Euler's identity, expanding this guy out in the middle and then taking the real part of it. So that's pretty obvious. This last one is just sort of a mathematical exercise in complex variables, and a real quick hint on that one is you want to show what value of theta can make the complex number on the left equal minus the square root of 2. So just think, where does minus square root of 2 sit? It sits over on this side. What's the magnitude of 1 plus j? That's a complex number, right? So what's the magnitude of 1 plus j? The magnitude is the square root of the sum of the squares of the real and imaginary parts. So what is it? Okay, so the magnitude is sitting at square root of 2, but there's an angle associated with that number. What's the angle of that number? If it's 1 plus j1, where does it sit in the complex plane? Where does it sits on that circle, right? Because it's magnitude of square root of 2. So where does it sit? Sits right there, doesn't it? Isn't that exactly where it sits, right on that circle? So now you can see that the answer is pretty easy because the e to the j theta is just going to multiply that complex number, and what's it going to do? It's only going to modify its phase because it's just adding theta. So you can just rotate that around. This thing can be made to rotate around on a circle of radius square root of 2 to any place in the complex plane that lies on that circle. And in particular, you want to rotate it around so it sits over here. Looks pretty doable, doesn't it? As a matter of fact, it doesn't even look like it's unique because you can find different values of theta that will all still put it at the same location. I think I've said more than enough. If you didn't absorb all of this, come back and look at the video when I get that posted tomorrow morning. You can look at it again. Just expanding your way of thinking of complex numbers a little bit to working some other exercises. So the quiz is going to be like 3, 4, or 5, that type of problem, or like the, related to the example problem or worksheet problem we just went through. So now we'll go into this new chapter. The title of the chapter is Spectrum Representation. So that's just continuing from where we left off in Chapter 2. We got motivated to look at the spectrum when we listened to the tuning fork and we did the spectrum analysis on it using some tools in MATLAB and saw that, the tuning fork doesn't just produce the fundamental, it produces some other harmonics. So generalizing that even further, it would be possible then to have a waveform like this that's composed of multiple sinusoids all having different amplitudes, frequencies, and phases. So that's what we formulated here. Different amplitude, frequency, and phase for each of the sinusoids forming the signal, and that's a function that you write in this first lab in MATLAB, something that can do that type of waveform generation. And then another term that's thrown in here is this A0, and all A0 is a constant. So if the waveform is squiggling around, the A0 just raises it or lowers it by what electrical engineers would call a DC offset. DC offset as in a bias type term that might be applied through a power supply or a voltage in an electronic circuit. We can just raise or lower a waveform that we view in the time domain. And that's very common in electronics, that a bias has to be present on a signal. Okay, we could do a complex sinusoid representation, which is the next form, and then just take the real part of the sum of complex sinusoids, and then these x sub k's could be written like we were just doing in the phasor addition formula as an ak e to the j phi k. The phasor addition formula, though, is not going to be helpful in this problem because f sub k's are not equal. Remember, in the phasor addition formula, the AK and the phi k's were all different, but the f sub k's were all the same, like all 440. We can't superimpose and get the phasor addition formula to work for different frequencies, but it's still a useful formula in a lot of other ways, but in this case we don't use it to our advantage because we're at different frequencies. But what we're desiring initially is the spectrum representation. So we want to be able to have a display, kind of like what that MATLAB display is, that shows us quickly what the frequency content is of a waveform composed of multiple sinusoids, be able to show the amplitudes of the individual terms and the phases of the individual terms. So we'll actually get two spectral representations, one that's called the amplitude spectrum and another one called the phase spectrum. But to make this fit with the mathematics, last time I was talking about negative frequencies and how that was going to show up very soon, and here it is. If we do Euler's identity on the cosine, then we can write out the cosine in this form right here. So in other words, if we had cosine x, Euler's identity says that that is e to the jx plus e to the minus jx over 2. And in this case, x is equal to 2 pi fk t plus phi sub k. Maybe it's theta sub k. What is it up here? Phi sub k. Actually, I picked a bad variable name there because we're using x for something else. So let me just change that. Use the Greek letter psi, just for variety's sake. Looks like a pitchfork, but it's called psi, PSI. We don't have a lot of fraternities on this campus. I don't know if we have any right now, actually, social fraternities. Are there any? There's 2? Okay. Well, fraternities, by historical reasons, learning the Greek alphabet was always important if you were in a fraternity, is my understanding. I was not in a social fraternity. I was in an honor society type fraternity, but I had a roommate my freshman year that pledged to fraternity, and it wasn't always a pleasant experience to be his roommate. But I won't go into those details. You can come and ask me about it sometime, though. It's a hard life, though, or it was a hard life for him, let's put it that way. So Euler's identity expands it into these 2 complex sinusoids, and it's the negative sign over here that is the big deal. That means we have complex sinusoids inside of here, that one is rotating counterclockwise, so it's a positive frequency, and the other one is rotating clockwise, so it's a negative frequency. So one is rotating like that, and the other one's rotating in the opposite direction. So this guy here is at positive frequency, and this one, because of the negative sign, is at a negative frequency. So in our spectral representation, we're going to end up having a spectral representation that sweeps from positive to negative frequencies. So we'll have spectral information on both positive and negative frequencies, which, as I said last time, is just for mathematical convenience and the way the mathematics works out nicely for all the modeling we want to do. When we display a spectrum, like what you saw in the previous chapter from MATLAB, it just displays everything on the positive frequency axis. But for certain types of signal modeling that's beyond the scope of this class, both positive and negative frequencies are used in a practical setting. It's just kind of the nature of the way things get dealt with in communications and signal processing applications, that the negative frequencies are represented uniquely from the positive ones. But we don't discuss any of those types of signals in this class as a matter of practice, because I don't want to get you bogged down in stuff that just, gets too confusing. There's plenty of other things to get confused on that are more important right now. So we have what's called the two-sided sinusoidal signal spectrum. And it's really very, very easy. It's just pairs of numbers. So we observe that the DC component, this guy sitting out here, if we were to do a spectral representation of that, we would just say it's a single spectral line on a frequency axis located at 0 frequency. So this is the frequency in hertz, and the amplitude of x0. When we look at what's present at frequency f1, we have something that's represented according to the modeling over here as x1 over 2, or x sub k over 2. And then at the corresponding negative frequency, minus f1, we have this x1 conjugate over 2. And so on as it builds out from 0, builds out spectral information. So these pairs, frequency amplitude pairs, as I've written them here, come from observing this mathematical expansion over here. If I scribble off all that stuff, we have one pair that's associated here with just 0 frequency, 0 hertz. And then we have the next set of pairs is these guys, the x sub k over 2 goes with f sub k, and then the x sub k conjugate over 2 goes with minus f sub k. Those are all pairs, though. They're amplitude and phases. The xk over 2 is complex, so it has magnitude and phase. So we have pairs, and that's the pairing that I have here in equation 3.3. So we plot the spectrum as vertical lines along the frequency axis, with the height being the magnitude or the phase. The book initially tries to put magnitude and phase on the same plot, but you can't do that in MATLAB. In other words, you can't draw a stick on a plot and have it have both magnitude and phase, unless you could have it sticking out of the page somehow to represent height and angle. So what the more common convention is to generate two types of plots, one that displays the magnitude of the xk and the other that displays the angle. And then it's called magnitude or phase plot or angle plot. So I guess, assuming you're reading the book, and I'd recommend that, just try not to get things confused. I will ask for a magnitude plot or a phase plot separately because I'm going to describe a tool here in a second that I've written in MATLAB that generates those plots for you once you enter the data into it, and it generates one of two types of plots. So here's an example of how we could construct the spectrum plot for this sum of a constant and two real sinusoids. We look at this representation in 3.4 and we see that we have a constant term of 5, and then we have a cosine term at 50 hertz, and it's got a magnitude of 3 and a phase of pi over 8. And then we have another cosine term at 300 hertz that has a magnitude of 6 and a phase of pi over 2. So if you expand that out using Euler's identity, inverse identity, which is in the next equation there, you can see that the constant doesn't expand at all, but that first cosine breaks into the two complex sinusoids, one spinning counterclockwise, the other clockwise, so one out of positive, one out of negative. And then the second sinusoid breaks down into these two terms. And then we just get the frequency pairs, the pairs from that, the frequency and the amplitudes from that. So here's the pairing right here. 0 hertz. At 0 hertz we have a 5, amplitude 5 for the spectrum. At 50 hertz we have an amplitude 1.5 and a phase of pi over 8. At minus 50 we have amplitude of 1.5 and minus pi over 8, and so on. And the big difference in plotting these pairs out is to notice that because of Euler's inverse identity, all the amplitudes of the cosine terms get reduced by 2. What happens is we take an individual sinusoidal term and look at its spectrum on the frequency axis here, f. We're basically saying if we have a cosine omega naught t, the spectral representation says that we put an amplitude of a over 2 at f naught and another spectral line at minus f naught of amplitude a over 2. So the height of the cosine wave has got a peak value of a, but when we do its spectral representations, like half of it goes at the positive frequency and the other half goes at the negative, and that's because of the way Euler's inverse identity works. It puts that one half in there. And in actuality, now you can kind of get an idea of how we can do a single-sided plot from this. If you do a single-sided plot of the magnitude, you just fold the negative side up onto the positive axis, and then the amplitudes would double again, right? So we would say if we just wanted to have the simple one-sided spectrum, we could just fold it up and we'd have a height A at f naught, and we'd be ignoring the fact that it actually was the mirror image we brought up from the minus f naught. But when we talk about two-sided line spectra, and that's what the book has you do, and that's what I want you to do, it's always split like this. This is a really big deal because when I give you a quiz on this, a lot of you are going to, if you're careless, you're going to forget that factor of 2. You're going to put, oh, you'll go like this, and you'll give me the result. Suppose this was 100. I'll see 100 sitting here, and that's not right. What should it be? 50. You'll be mad because you made a simple algebra error, not a calculus error, right? Which are more painful or more acceptable for you guys these days? Algebra errors are supposed to be from high school, I guess. Calculus errors, you'll accept them probably and say, well, I'm just not an expert yet, but algebra errors are upsetting. Or when I had advanced calculus, when I was working on my doctorate, I had a guy with a thick Missouri accent, and he couldn't help but say algebra because he just, people in certain parts of the country, as you head south, they kind of have sort of a garbling up sound, and so I took that as meaning to saying that algebra is boring because it sounded like he was saying algebra. I can't say it exactly, but he also would talk about drinking several sodies. So that translates to me, being from Wisconsin, as several pops, because pop is what we called it in where I grew up. But there's more stories on that, right? If you're from the South, my brother lives down there, and everything is a Coke, whether it's a Pepsi or a Sprite or an orange. Is that true? Why is that? I don't know. That's historical, I think. Okay, here's a function that I wrote that can take the data from equation 3.6 and just make nice pictures in MATLAB. I'll let you study the code itself to see how I wrote it, and you can maybe learn something. But here I just enter in the data that we just went through. So I have one vector that takes in all the frequencies, the 0, 50, and 300 hertz. And then I have to enter in the magnitudes and phases of each of the components. So I have this set up so you don't have to enter in the positive and negative frequencies. You just enter in the DC term, and then if you enter in a complex quantity over here, you just enter it in once, and it automatically knows that it has to plot that at the positive and negative locations and incorporate what? If I put in a 3 there, what's it going to have to do to plot it properly? Divide by 2. So we'll do that automatically. Or maybe it doesn't do that. Yeah, it does do that. So that's at, the second term here is at 50, so that's these lines right in here. And then the third term is entered in here. And then I just have a final entry into this is in single quotes. That's the way MATLAB does string variables, that I want mag or phase. And so here it generated the magnitude plot versus frequency. And then if I kicked it into gear to do phase, it generates the phase plot. Okay. Nothing to deal with this until the next homework assignment, which I'll post soon. Nothing to do with this until we get to the next lab. So now what I want to do is slide ahead on some stuff that's interesting and is going to show up in the next lab, but it doesn't help us finish the first lab. So it's just kind of orderings that I've learned by practice, but I haven't redone the notes. So one of the things that's already in the second sign-off of the first lab is this topic of periodic waveforms. When you have multiple sinusoids at different frequencies, it's possible that you still have a periodic waveform. And some of you did this already last Friday. You put together that composition of a constant and 2 cosine waves, and you looked at the picture, and you were able to see that it's periodic, right? How many people saw that already on Friday? I saw it on screens when I was walking around, so I know some of you did it. What makes that sort of a signal periodic, or how can you figure out the period of that theoretically? In MATLAB, you can do it experimentally, but the problem also asks you to do it theoretically. So how do we get that theoretically? Well, first off, to be periodic, we have to have this true. We have to be able to say that x at t is equal to x at t plus t naught or t minus t naught, where t naught is the smallest value that makes that equality hold. That would be the fundamental period. 1 over the fundamental period is the fundamental frequency. So f naught, the fundamental frequency, is 1 over t naught. Skip this little example and just continue with the thought. Suppose we have a signal composed of multiple sinusoids, all at harmonic frequencies. Harmonic frequencies mean that the frequencies in equation 320 there are all multiples of each other. There's some underlying fundamental, but they're related through integers. So there's an f naught and then there's an integer times each one in the term, some different integer value. The fundamental frequency is f naught. So the mathematics to make this a periodic signal, and this applies to that problem in the lab, is that the fundamental frequency f naught is the greatest common divisor of all the frequencies making up the signal, exclusive of DC. If there's a DC or constant term, that doesn't matter because that just raises or lowers the waveform. It doesn't change anything with the periodicity. But of the terms that are frequencies, like suppose we had 2 hertz and 18 hertz, what's the greatest common divisor of that? That's 2. So that's the fundamental. That's the fundamental frequency. So what is 18 hertz in a harmonic sense? Which harmonic is that? The fundamental is the first harmonic. So 18 is what integer times 2? 9th, right? So it's the 9th harmonic. Suppose you had this poor situation. I say poor because prime numbers have a certain property. They're not related by any divisions or multiplication. So if I had 3, 7, and 9 hertz in a system, the fundamental there is going to be 1 hertz because I can derive 3, 7, and 9 by direct multiples of 1 hertz. Make sense? What happens if I had 20.25 and 21 hertz? If I had those two signals present at the same time, are they harmonically related? And what's the fundamental frequency? Okay, you say 0.25. I just pulled this off the top of my head. I'm pretty sure that's what it is, but it might be 0.5. I don't think it is, though. Let's see. All you have to do to get this to work out with this greatest common divisor is you can just go 2025, 2100 and do the greatest common divisor on that to get the answer. And then you have to divide by 100 there again and get it scaled back. But so suppose, and I have to think on this, I don't want to work my brain too hard right now. Actually, I could do that. I have Mathematica running, but I want to talk about something else. Suppose it is 20.25 hertz, then to figure out the harmonics that 20.25 and 21 are of that, you would just divide 0.25 into 20.25 and you get that integer and do the same with 21. And then those would be very high order harmonics. Is that the correct? It's 0.75? That's the GCD? Okay. So F naught is 0.75 hertz. When we get into the lab tomorrow on Friday, I'll show you how this works, and you can use it immediately to find the period then. Because if you find the fundamental frequency, then you've found the fundamental period, right, by just taking the inverse. And that's what they ask you to do for that second sign-off. Some of you are nodding your heads like you know what I'm talking about. Others of you, when you read down further in the lab on Friday, you'll get there and then you'll be able to plug into this equation. The significance of having it periodic or not periodic, I did a little example here in MATLAB. We're going to learn about Fourier series eventually here too, but here's a little dramatization, you might say. I've got three sinusoids that I added up, one at 100, one at 300, and one at 500. Those are obviously harmonically related. They're first, third, and fifth harmonics. And the amplitudes go 1, 1/3, 1/5. EEs learn, after this class in particular, that that sort of a series, if you keep continuing it, forms what's called a square wave. Just three terms in that series expansion give us this wiggly-looking square wave. A square wave is just something you've learned about clock signals in logic circuits, so you know what a square wave is. This is an approximation to a square wave just using three terms of a Fourier series. And we're going to be studying that more. Is that exciting or sounds too mathematical? You'd say, oh, it's a clock. But a clock signal can be written in a Fourier representation. But just to see what happens, I tweaked those frequencies ever so slightly away from being harmonically related. I made them square roots of some numbers that were just one integer away from being a perfect square. So instead of being 300, it's the square root of 89999, which is not quite 300. Get the idea? Then I draw the picture of it, add them all up. Not periodic, right? You study that with your eye and you see, does that ever repeat? And I'm hard-pressed to see that it repeats. It's because all three of those sinusoids are at slightly different harmonic frequencies, and they're kind of asynchronously sliding through, and they're never going to create a repeating pattern. We do more of this studying in this chapter, those types of ideas. Okay, next big concept I want to spend some time on, though, is over here in Lab 2B. You get down to this last part, and this is what I'm going to be demoing as a live demo, direction finding with microphones. You've got this situation where you put up two receivers, and I'll have an array with two microphones on it, which will be represented here in the geometry of the problem. And electromagnetic waves could be used for direction finding if the vehicle was transmitting a steady carrier signal. To make it more physically understandable at this time, we're assuming that the vehicle that's driving down the road there with a certain velocity, but actually is just fixed at location XV right now, is emitting a 400 hertz tone. And by setting up this microphone array off axis from the highway, we are able to get the angle of that vehicle by just working with the received signals at the two microphones, 1 and 2. This can be done using, like I said, electromagnetic waves, so it's using an antenna array that has two elements, and you can direction find on a signal. And you know this can be done, right? They do it in movies all the time. It must be possible from electrical engineering principles and physics to locate people. GPS satellites locate people too. So, at any rate, some of the themes of this are the velocity propagation of sound waves is 333 1/3 meters per second, so it's rather slow. But they ask you a bunch of questions over here. They ask you to model the signals received at the microphones as just time-delayed versions of the emitted signal, which is the 400 hertz tone. So we've studied this type of representation where you delay a signal by T1 and T2 seconds. Then they come up with this neat formula down here, which says that if you know the time delay between the arrival of the two signals, you can calculate the angle off of the normal on that array to the target. So they have this formula, d over c sine theta is equal to T1 minus T2. how does that come into being? Well, if you go onto the website, underneath the folder, if you link to the folder, you can download this little drawing that I made a few years back. It's called Direction of Arrival Approximation. So it's just trying to show you mathematically that if you think of a source being a long ways away from the microphones, remember I talked about plane waves a little bit last time. When a source emits a waveform, the wavefront goes out in what shape? If I'm just an ideal point radiating sound or an electromagnetic wave, how does it radiate? It's spherical, right? It just goes out as a sphere, or think of a pebble in water. It sends out a circular wavefront. But when you get far enough away from that source, does that front look spherical or planar? It looks planar. So the model that's used in this project is assuming that it's a long ways away, so it's assuming that it looks planar by the time it arrives. So I've tried to show that in the picture. I've shown it as the source not emitting a spherical wavefront, but it's far enough away, the distance is long enough that it looks just like a plane wave traveling like that. So when we look at the geometry way over here at the receiver, we basically have this simplified geometry which says that in this particular alignment, the signal first arrives at sensor 2 if it's a plane wave coming in, and then it takes d sine theta. It travels an additional distance of d sine theta to get to the first sensor. And working from the geometry, the angle to the target is theta off of the normal angle to the array. But from similar triangles, theta is that interior angle in there. So d sine theta is the projection then of the hypotenuse of this triangle through that angle theta down onto that base of the right triangle. So that's the basis for that equation that appears to relate the time differences. Now the question is, how do we do some of the math? So if you, I know I'm basically out of time here, but we have two sensors up here and here. Then we have our target out here at xv. This is located at y sub r, and this is a distance d away. So the first question they ask you is, what are the distances, those two distances? Call this one r1 and call that one r2. So as an example, what's r1 going to be? R1 is, from geometry, xv squared plus y sub r squared, right? You know, the two sides of the triangle. What's r2 going to be? Well, that's this little triangle in here. So what's the base on that triangle? Okay, xv minus d squared, then still yr squared. Now what about time delay? Time delay, t sub delay of a propagating wave is always the distance d or r over what? The velocity of propagation. Does that make sense just from physics? R is meters, c is meters per second, so the units work out to be seconds, which is time delay. So that works out. So that has units of seconds. So we just plug into this equation and we have time delay 1, which they ask you to solve for. T1 is going to be R1 over C, and R1 is this guy up above here over C. And you do this for the rest of the math and it all kind of comes together. I wish I would have had a little bit more time, but we're about out of time for class. This factors into the very last grand finale in the lab, which is applying a whole bunch of ideas that we've learned about into one. And phasor signal modeling shows up in here too. Maybe what I'll do is I will take my notes page and hand that out on Friday to help you with some additional notes or post it or something for working that. Same routine. The quiz will be the first thing on Friday.